Draw a circle. Now try to build a square with exactly the same area, same amount of space inside, using only a compass and an unmarked straightedge. No rulers with numbers. No calculators. Just circles and lines. The Greeks called it squaring the circle. It sounds like a geometry homework problem. It became one of the longest-running puzzles in mathematics. Most people guess nobody found the right construction yet, that a clever enough diagram will crack it eventually. The math says otherwise. Squaring the circle is not hard. It is impossible with compass and straightedge. Not because ancient Greeks lacked patience, because the number pi is the wrong kind of number for these tools to reach. Compass and straightedge is not a random restriction. It is a game with strict rules. The compass draws circles from a center to a point. The straightedge connects points with straight lines, but it cannot measure distance. You may copy lengths by swinging arcs, but you never read a number off the page. Every construction must be built from those moves alone. A circle with radius 1 has area pi. A matching square needs side length root pi, because root pi squared equals pi. So squaring the circle secretly asks a sharper question. Can you construct a segment of length root pi using only compass and straightedge? If you cannot build that length, you cannot build the square. The whole puzzle collapses to one number. Greek mathematicians took the challenge seriously. Hippocrates showed you could square certain curved shapes called lunes, crescent moons made from circles. That success made squaring the full circle feel close. Archimedes trapped pi between fractions. Generation after generation refined approximations. But approximation is not construction. Getting close is not the same as building exact length. Here is what compass and straightedge are good at. Start with a unit length. Mark points. Draw lines and circles. New intersection points create new distances. Every distance you can reach this way is algebraic. It solves some polynomial equation with whole number coefficients. Square roots, cube roots of rationals, nested radicals, all fair game. The tools build algebra, not every real number. Pi is transcendental. That is a technical label with a plain meaning. Pi is not the root of any polynomial with integer coefficients. It sits outside the algebraic world that compass and straightedge can reach. And if pi is transcendental, so is root pi. You cannot construct what the tools were never designed to produce, no matter how many centuries you spend drawing. In 1882, Ferdinand von Lindemann proved pi is transcendental. That closed the classical problem. Squaring the circle was not waiting for a genius diagram. It was waiting for a classification of pi itself. The proof is deep, but the headline is simple. Compass and straightedge cannot square the circle because they cannot construct root pi. The game rules decide the answer. Here is the surprise. People kept trying because the tools feel powerful. You can bisect angles, erect perpendiculars, even build regular pentagons. But three famous Greek requests all fail for the same family of reasons: trisecting the general angle, doubling the cube, and squaring the circle. Not unlucky, not unfinished. Impossible under the stated rules, and the rules are the entire question. Relax the rules, and the story changes. Marked rulers, paper folding, or calculus can achieve constructions impossible classically. But that is a different game with different tools. The classical problem is not, can humans make a squarish shape? It is, can these two instruments, alone, produce root pi? Under those rules, the diagram has been complete since the 19th century. Recap. Squaring the circle means building a square with area pi. That requires constructing root pi. Compass and straightedge only reach algebraic lengths. Pi is transcendental, outside that reach. Lindemann proved it in 1882. The Greeks were not failing at a homework problem. They were exploring the boundary of what two classical tools can create. Some puzzles end when someone draws the right line. This one ended when someone classified the right number. Next time on Math Sketch, the hidden patterns inside Pascal's triangle, where combinations, fractals, and probability all hide in plain sight. Subscribe for weekly pattern hunts. This is Math Sketch.